Last video of the first day of week 2, so the halfway spot. So we're going to talk about oxygen, carbon dioxide transport, and a lot of this should be review. All right, so here are the topics and outcomes for this. So if you remember, we transport oxygen 2 ways in our bloodstream. Overwhelming majority is bound to hemoglobin, the rest is dissolved in plasma. Now we can see the relationship between the amount dissolved in plasma and the amount bound to hemoglobin, or hemoglobin saturation. We've got the oxyhemoglobin dissociation curve. So partial pressure of oxygen on the x-axis, which corresponds to the amount dissolved in plasma. And then the percent saturation, which corresponds to the amount bound to hemoglobin. Okay, notice that this curve is kind of sigmoidal, not kind of, it is sigmoidal in shape. Okay, and so we've got this steep part and then we've got this flat part. Now we are typically at about 100 here, which corresponds to about 95, 96, 97, 98%, somewhere in there. Now, as you can see, we can shift this curve right or left. Now, the effect of a right shift, so these are the causes, these 3 things that increase, or we can or it can decrease. Those are all causes. Okay, the effect of a right shift is that we have reduced affinity. Okay, and so let me rephrase this here. So the left shift, we decrease any of acidity, temperature, or carbon dioxide. On that figure, there was also something called 2,3-DP or BPG. That's something we'll talk about during our altitude lectures in a couple weeks. What if we have decreased acidity, temperature, or carbon dioxide, that increases the affinity or attraction between oxygen and hemoglobin. In other words, we're making it so they want to get together. So oxygen and hemoglobin bind together, or oxygen is loaded onto hemoglobin. Right shift is the exact opposite. If we have high acidity, high temperature, high carbon dioxide, or high 2,3-DPG, that decreases the affinity. Remember, the top bullet is the cause, the bottom bullet is the effect. Okay, and this ties into our Bohr and Haldane effects. So Bohr effect is saying that if we have high carbon dioxide, there's not going to be as much affinity or attraction between hemoglobin and oxygen. And an easy way to think of this is just think of a classroom. And think of all the chairs that are in the classroom, and each chair represents a binding spot for hemoglobin and oxygen. Well, if let's just say that the faculty members represent carbon dioxide, well, if they're all sitting in the chairs, for every chair that they're sitting in, that is one less chair that's available to the students that we'll use as oxygen in this little analogy. Okay, and so if I have lots of faculty, or in other words, I have a high amount of carbon dioxide, there's less binding spots or less ability for oxygen and hemoglobin to bind, and this is what occurs naturally in the tissues. The Haldane effect is the exact opposite. In this case, if I have lots of oxygen, so I have lots of students sitting in the chairs, there are fewer chairs for faculty to sit. Okay, and so as a result, there's nowhere, or there's less places for carbon dioxide to go, and this occurs in the lungs, which is great because we're trying to exhale carbon dioxide and we don't want it to be bound to hemoglobin. Now, when it comes to our blood, there is a finite amount of oxygen it can carry. And this amount is determined by a few things. The hemoglobin concentration, remember that's generally higher in men than women due to the menstrual cycle, the saturation of hemoglobin, and the partial pressure of oxygen that's in the arteries. And so we can calculate the capacity by using the following equation. Okay, 1.34 milliliters of oxygen per gram of hemoglobin times the hemoglobin concentration times the saturation. Okay, and all that part on the left, that's all accounting for the oxygen that's bound to hemoglobin. And then we've got the right side, which is plus 0.003 times the partial pressure of oxygen. Okay, ultimately, if we're calculating capacity, we just set saturation to 100%. Okay? So there's going to be a difference between capacity and actual content. All right, so in this case, we can carry 20.1 milliliters of oxygen per deciliter of blood on hemoglobin, and then it's 0.3 of a milliliter of oxygen per deciliter of blood in the plasma. Now, when it comes to content, it's the exact same thing, but instead of using 100% for saturation, we use whatever the actual saturation is. And so let's just say it's 98, which is a typical, normal, actual value. You can't ever be 100% saturated. And so what happens is that we end up with 20 milliliters of oxygen per deciliter of blood. 19.7 coming from hemoglobin, 0.3 coming from plasma. Remember, like I said a moment ago, hemoglobin concentration is almost always lower in females or people with sickle cell. In cases like this, it doesn't make a huge deal unless we're using or we're performing, or these people are performing high intensity in aerobic activities. So think like end of a VO2 max test. Now, ultimately, what's important is how much oxygen are we delivering? And it's a real simple equation. I take my content, I multiply that by cardiac output. So from our last slide, if I have 20 milliliters of oxygen per deciliter of blood, and let's say my cardiac output is 5 liters a minute, or 5 liters of blood per minute, well, we got to change units. So there are 10 deciliters in a liter. So that would mean that my 20 becomes 200 milliliters of oxygen per liter of blood. I multiply that by my 5 liters of blood, and I end up delivering 1 liter of oxygen per minute. That's typical resting values. This is higher than VO2 because we don't use all of the oxygen that we deliver. Okay, but that's the most that we can deliver under that condition. Now, obviously, if I increase my cardiac output by 5-fold, then my oxygen delivery will increase by 5-fold. So if that 5 becomes 25, that will mean my 1 liter of oxygen per minute becomes 5 liters of oxygen per minute. Now, when it comes to carbon dioxide transport, we transport it in 3 ways: plasma and hemoglobin, but most of it is transported as bicarbonate. So hopefully you remember this equation from your physiology class. So when we combine carbon dioxide and water with the help of an enzyme called carbonic anhydrase, that will form carbonic acid, ultimately leading to hydrogen ion and bicarbonate. Now, we want this equation to go to the right in the tissues because that's how we transport most of our CO2. We don't want it bound to hemoglobin because we want those spots available for oxygen. All right, but in the alveoli, we actually shift this equation to the left so we can create CO2 so we can exhale it through the airways. Okay, remember that this equation is used for acid-base balance. Carbon dioxide is acidic, bicarbonate is alkaline, and depending on what's going on, we can shift this equation to compensate for changes in pH. So if my arterial pH exceeds 7.45, meaning I'm alkaline, I'm going to shift it to the left to create CO2, which is in essence an acid. However, if I'm acidic, I have a pH lower than 7.35, I'm going to shift this equation to the right to get rid of CO2 and form bicarbonate. And this relates to something called the ventilatory threshold, which ties in pretty closely to the lactate threshold. We start hyperventilating during intense exercise because we become acidic. So, what do you need to be able to do? Identify the primary ways that oxygen and carbon dioxide are transported in the blood. Use the oxyhemoglobin curve and explain how the curve can be shifted and the effects of those shifts. And then describe the difference between content, carrying capacity, and delivery.